Okay, so I got Eclipse working, no problems. So first thing you want to do is create an empty class with a main method, and for now we just need main. We won't need to set up classes and things like that. So what kinds of variables can we have? We can have int I and assign a value to it at this right when we declare it, so that's called a declaration, and then initializing a variable. And we can print it out. I'm hoping this is all something we can do. System.out.println is the most straightforward way, if you can spell it. Oops, now I'm stuck. Alright. I'll check my spelling too. Alright, system.out.println, and you can say I is, does not seem correct grammar, but it's perfectly fine. Right, and we'll print out I. We're printing out the value of this variable I. Save it, and you guys probably know that as soon as you save it, the Java compiler kicks in and compiles a program, and then we can click on this to run it. Okay, so there it goes, and it prints out I equals 0. So you can set this up to be anything. You can have any value, almost any value. You'll see the limits. What can we assign any value to an int, for example? It turns out no. There are certain limitations, and so we have to look at what are those limitations, because to those limits. Alright, so we can have an int I equals whatever. I print it out. It can be positive or negative. Save it. Run it, and it should work. And you can have a whole expression over here. You can say 109 divided by whatever, 30. And run this. And since we're dealing with ints, of course, we can only print ints, even though technically speaking, if you're just looking at numbers, 109 divided by 30 will give you a fractional part. Of course, those things, the fractional part is thrown away in for integer operations. Why is that? Because when you do an operation like this, you're using hardware in the end, and the specific part of the hardware that you're using is called an integer arithmetic logic unit in this case. So an integer arithmetic logic unit takes two ints, like minus 109 and positive 30 as the two inputs. It performs an integer division in hardware and then gives you a result, which is an int in this case, because we're using an integer arithmetic logic unit in the hardware. That int is stored into this variable I. Okay, so that's why when we print it out, we don't get 3 point something, we get exactly -3. Okay, so what are the rules for identifiers? Can we set up anything? No, you can't say int if is equal to 5. If you do that, you'll get an error message, and Eclipse sort of helps you along. It shows you that all of the keywords are, most keywords are in purple in Eclipse, and so this is not, purple is not like an official Java color. It just so happens to be what Eclipse uses. So if you try to do this, you'll get an error message and you can cancel. What about something like this, $_? Turns out that is perfectly fine. You can have variables like $_. You shouldn't, because that's hard to read. You don't want to make people read code with variable names like that. So $_ is, and we can print it out. If you don't believe me, try it. Okay, save it, run it, and there it is. Dollar underscore is 5. You can even make it just dollar, just plain dollar. That's a valid name in Java. Seems like, it seems like that should not be a valid name, but unfortunately it is. So don't go out writing programs with dollar variables called dollar. Or you can do that, but let's not. So you can go ahead and try it out in Eclipse. Try to come up with different kinds of identifiers. Try using the dot operator inside a name. So int x.5 or something like x.5 or x-5. Those things are just not allowed. You can use underscores, but not minus or hyphen. Alright, next up, let's look at Java literal. So literal is a representation of a value. So 5 is just a representation of the number 5, and it turns out internally Java does not represent it exactly as shown here. So for ints, for simple ints, sure, that's fine. A 5 is exactly represented as a 5. However, for floating point numbers, what we will see is that literal constants like 3.1415 may not be exactly 3.1415. It might be 3.14150000, many zeros and then a 1. That is possible. Why? Because there's this thing called round off. We only have finite precision in Java, and we cannot actually have every single real number represented in floating point number because there is an infinite number of real numbers. There's no way computers can represent that. You would take all of all of the memory of all of the computers in the world and still not be able to represent all real numbers because there's an infinite number of them. Okay, so we have limitations for double precision or single precision floating point numbers. You can have literal constants like a string, in this case hello, or you can have a single character in single quotes for a single character, double quotes for string. Okay, I'm hoping this is all just review, that you've seen all of this. Integer literals are pretty straightforward. They just look like decimal numbers usually. So there's an important caveat down here. But let's first take a look at the straightforward number is 25 is a number, 0 is a number. 1, 2, 3, 4, 5, 6 is valid. Let me see this. Yeah, you can have bigger numbers than this, but eventually you'll come up to a limit that you can put in an int. So these are all valid. You can have negative signs. A unary a minus sign just before a number will flip the sign of the number. And you do not, integer literals should not contain commas or decimal points. And you should not have leading zeros unless you know what you're doing. So it turns out you can do something like this. You can't say int something equals 050, but when you print it out, you'll get a surprise. So let's try it out. So I'm gonna get rid of some of this old code. I'm hoping everybody's fine with this. Just set up a simple example. Let's do 40. Okay. No, 50. 50 might be easier to understand. All right. So we say int I is equal to 50. We print it out. We get I equals 50. I is 50. No surprises. Put a leading 0. That's what it's called. Put a leading 0 there, and notice what you get. You get I is 40. So I'll give you a few minutes to maybe figure it out. You can pause the video if you want to figure out why putting a 0 here gets you 40. Taking it out gives you 50. Okay, so assuming that you try to figure it out on your own, you pause the video. I can tell you the secret. The secret is, it's not a big secret. It's just that when you put a 0 in front of a number before something that's non-zero, like 1, 2, 3, 4, 5, 6, 7, 8, 9, then you're saying that you want this number not to be a decimal number that is base 10, but base 8. And that's why you get a 40 here. because this is saying, okay, now this number, this whole number, the rest of this is base 8. And what that means is I'm going to take 0 times 8 to the power 0, which is 1, and that'll give us 0, plus 5 times 8 to the power, 5 times 8 to the power 1, which is 40, and you add up everything, and that's why you get 40. So once again, this is base 8. You can also do base 16. So base 8 and base 16 are numbers that computer scientists like to use, and so you do base 16 by putting an x, 0x. And I can pause the video. You can pause the video and try to guess what this will print out. So try to guess, and assuming that you've tried it out or paused the video and figured it out, here's the answer. You get I is 80. So you can try to work on that, figure it out. I'll tell you the reason for this. You're now, when you use 0x in front of a number, you're using base 16. Very useful thing for computer science. So you're saying 0 times 16 to the power 0 is 0, and then 5 times 16 to the power 1 is 80, and that's why you get an 80 here. Okay, and you can mess around, you can try different things. 51 should give you 81. Yeah, that's not so hard. Okay, there we go. And it turns out you can also go all the way up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This will give you 89. And then here's the surprise, you can say A. So A stands for 10. And so this should give us 90. And then after A comes B, which will be 91, C, 92, 93, 94, and 95. And let's try it. F will give us 15 plus 5 times 10 to the power 5 times 16 to the power 1 will give us 95. So are we going to use hexadecimal? It's very unlikely. The place where you will see that is if you take the junior level course Computer Organization, and where we learn things like assembly language programming. Okay, so let's go back, and this is a good thing to know. Will I test you on this? No, I won't test you on this, but it's just one of those things you want to, makes you think about what literals are. What are literals? Why is a 50 different from a 050? So those are good things to think about. Floating point literals are pretty straightforward. Any number that includes a decimal point is automatically assumed to be a double precision number, not a float. So what is the difference between a double and a float? Turns out float is 4 bytes and is considered standard precision, and then a double is double the size of a float. The amount of precision goes by more than a double, and it more than doubles the precision, going from 4 bytes to 8 bytes. But this nomenclature came about, what, 30, 40 years ago, and we've stuck with it. Double stands for double the precision of a float, which is considered single precision. Okay, and then we can also use exponential notation. This just means 0.5 times 10 to the power 3. This is 0.5 times 10 to the power minus 3, or 0.0005. Okay, so I'm hoping that you guys are familiar with that. You can use uppercase E2, which means the same thing as this. And you can use exponential notation without the decimal point. It is still a double. So if you use the E, it becomes a double. If you use the decimal point, it's a double. And you can use 2.0, however many digits after the decimal, and exponent minus 27. And so you might want to try this out. This is pretty straightforward. There's no trick to this.